In this video project, or this video I'm going to show, I wanted to see how much I could learn about Coriolis effect. Coriolis effect is something that a lot of us, or most of us, have heard about occasionally as we go through life, and we see some sort of sniper video game or sniper movie, or we hear somebody talking about dropping artillery shells. So, as with all my videos, I don't like not knowing stuff. I like to try to figure stuff out. So I like to know stuff, and I also just like to figure out puzzles. So that's what this is. In the video game Call of Duty Modern Warfare, the guy mentions he has to use Coriolis effect or consider that when shooting the bad guy. They were unloading a bunch of blocks of gold or something. So maybe sometime I'll make a video to see what kind of Coriolis effect there would be there. So right here we have a circle, that's the Earth. Right here at 0 degrees is the equator, and then up here I have 30 degrees. So if there's a person on the equator right here, they're spinning around the Earth at a certain velocity. If there's a person on the Earth up here at 30 degrees, they are spinning around the Earth with a less velocity because they are effectively on a disk that's smaller. So I found out what you can do, at least logically, at least this is what it looks like. You can take the Earth and just divide it up into a bunch of disks, like records playing on a record player or a merry-go-round or something. And say there's a person on this large disk right here at 0 degrees, the equator, and they're going to shoot at something at the 30-degree mark right here. Maybe it's a long-range sniper shot, maybe it's an artillery shell. But the people on this large disk at the equator are spinning faster as they shoot toward the pole. So this is like a two-train scenario where you're on one train that's moving fast. If you're at the equator, you're going to shoot at another train that's moving slower. So in that case, you need to lag the target or shoot behind it, aim behind it, and then effectively your bullet will curve and hit the target. The bullet won't curve from your perspective, but it'll curve from their perspective. And likewise, if you're shooting, say, from the pole towards the equator, you're on a small disc shooting towards the large disc, so you'll need to lead the target. So what I was curious about was, if I was in a situation where I was in charge of some sort of artillery, like the M777 or something, and there were no computers to calculate for Coriolis effect or compensate for Coriolis effect, but I had the ability with that artillery to drop a shell anywhere I wanted within, say, 20,000 meters or 20 kilometers, which is about 12.4 miles. So say I had a map of the region. Say I'm at the equator right here and I'm shooting toward the 30-degree mark right there. And I have the ability to point that howitzer anywhere I want and drop a shell on any location I want if I look at that location on a map. So my question was, would I be able to do the math to at least get a rough idea of how much the Coriolis effect is going to matter and where I should aim that howitzer? So that's what this video is about. It looks like all you have to have is just some high school trig, basic SOHCAHTOA stuff, meaning we don't have to deal with any complicated equations for sine waves or cosine waves or anything like that. We just look at the cosine of the angle. That will tell us the size of the disk that we are spinning on. So we use the angle to get the cosine. That cosine is also the radius of the disk that we are effectively spinning on. We turn radius into circumference. We turn circumference into velocity because we know how fast the Earth is spinning. And then basically we know the velocity difference between the two trains. If we're on a fast train and we're shooting at a slow-moving train, then we know how much to lag the target or lead the target if we're shooting at a faster train. Here's some things I learned. If I want to shoot at a target, say 20 kilometers away, which is about 12.4 miles, I should probably use the arc to measure that distance because that's what people would use in real life. They're going to say we're shooting at a target 20 kilometers away as you follow the arc of the circumference of the Earth. Previously, I wanted to use the sine value, which meant if I was shooting at a target 20 kilometers away, I would use that sine value to measure 20 kilometers on the sine, meaning that this leg of the triangle was 20 kilometers. But that's actually not accurate, because if you're down here near the equator, your sine value is only going to be slightly shorter than the arc of the circumference right here. But if you take that same length of that same sine value of 30 degrees and put it up here at a higher latitude near the North Pole, or near the top of the circle, you'll still have that same 20-kilometer sine length on your triangle right there, but that's going to cover a much larger distance as you go around the arc of the Earth right here, or the arc of that circle. So that was one mistake I made. Here's something we look at though, since we're just looking at cosine values, because a cosine value is the radius. It's the effective radius of the disk on which we are spinning. If you're near the equator, notice for any given angle, such as 30 degrees, your cosine value is almost identical to the full radius of the Earth. But now let's take this same 30-degree arc, and instead of going from 0 degrees to 30 degrees, let's go from 50 degrees to 80 degrees. So this is still a 30-degree angle right here, but notice the cosine value is vastly different. The cosine of 80 degrees is very tiny compared to the cosine of 50 degrees, which is much larger. And down here, the cosine of 30 degrees is only slightly shorter than the cosine of 0 degrees. What this tells us is, as you're near the equator and you're shooting either toward the pole or toward the equator, the difference in velocity between those two locations near the equator, basically there will be very little difference in velocity. They'll have almost identical velocities. But you go up here toward the pole, the same 30 degrees, and the person up here at 80 degrees is going to be spinning at a much lower velocity because their cosine is much less than the person at 50 degrees. So those are two things I learned. One is you shouldn't use sine value to measure the distance around the Earth, and the other is around the equator, the velocities are almost identical. In this situation, I'm talking about shooting between two different latitudes, either towards the pole or towards the equator. Toward the end of the video, I'll cover what happens if you're shooting roughly on the same latitude, which means if you're shooting directly east or west. And let's see what I say here. Okay, I just wrote here, huge difference in cosine between 50 and 80 degrees compared to 0 and 30 degrees. That little circle with the plus sign, that's a symbol for Earth. Radius, mean radius that is 6,371 kilometers. Times 2 pi gives you the circ, 40,030 kilometers. Feel free to plug in more accurate numbers if you want. These are just going to be approximations to give us an idea of what we're doing here. And remember, the Earth is an oblate spheroid, ever so slightly, because as it spins, it slightly bulges in the center. So I just calculated the arc length here between 0 and 30 degrees, or between 50 and 80 degrees. You just take theta over 360 equals the arc over the circ. So for example, if we're talking about 30 degrees, it goes 30, 60, 90. So 30 divided by 360 is the same thing as 1/12. Therefore, the arc right here will be 1/12 of the whole circumference. And I plugged in the numbers, so this arc length here, if we are shooting at a target 30 degrees away, that arc length will be 3,336 kilometers. I use large angles here, but in reality, if you're doing shooting just with dumb artillery, also known as unguided ordnance, I've read the maximum range on that is around 15 miles or so. So I chose 20 kilometers, which is 12.4 miles for the distance. So we're going to pretend that we are going to be in charge of shooting an artillery shell, and we have to decide how much to lead or lag the target. Right here I showed what it's actually going to look like though. If you're looking at something 20 kilometers away, it's basically the width of my ink pen right here, because 20 kilometers is very small compared to the radius of the Earth, which is 6,371 kilometers. And I said here 20 kilometers equals 12.4 miles. If we take 20 kilometers divided by the radius of the Earth, this is 3/1000ths approximately. So if we take the radius right here, this circle that I drew has a radius of 6 centimeters, which is 60 millimeters. And we divide this up into 1,000 segments, then 20 kilometers will be three of those little segments. To compare that to the ink line on the paper, my pen here is a 0.7 millimeter ink pen, if you can see that. So we take 0.7 divided by 60 millimeters for the radius, we get 0.01. So even this ink line right here is 1% of the radius, so it's actually much thicker than 20 kilometers would be on the same scale for the Earth. If you take 1% divided by 3/1000ths, then you'll get 3 times thicker. So this means the ink line is 3 times thicker than 20 kilometers would be on the Earth. I just wanted to show that because I like showing all these details to know exactly what it is that we're dealing with. And I tend to try to avoid making assumptions because a lot of times those assumptions are wrong. By the way, as with all my videos, these videos are kind of a two-part thing. First off, they are just complicated puzzles, or like a complicated scavenger hunt where each clue leads to another clue, and that's a lot of fun. But then also there tends to be a lot of math involved, and that's just part of the solving these equations. Most channels would skip over all this stuff, but I like to get down and show the nitty-gritty details because after all, that's how we solve these puzzles. So here, target is 20 kilometers away, or 12.4 miles. Theta over 360 equals the arc over the circ. That means theta equals 0.1798, yada yada degrees. I said here we take the angle theta, turn that into cos theta. Cos theta actually equals the radius that we're dealing with of the disk, the pretend disk that we're spinning on. And then we turn radius into circ and circ into velocity. Then we take the velocity difference between us and the target, and we know if we should lead or lag the target. And right here, cos of the angle is adjacent over height. So adjacent is 6,370. So what I did right here on this greatly exaggerated angle, I'm finding out how big the disk is at 0.1798 degrees. So the equator is at 0 degrees. I'm finding out the velocity if we are just above that at 0.1798 degrees. So the adjacent right here is our effective radius of the disk on which we are spinning. Multiply by 2 pi to get the circ. And then we multiply by 1,000 to turn kilometers into meters, divided by 60 seconds per minute, 60 minutes per hour, 24 hours per day. And the velocity that you're spinning at, if you are at 0.1798 degrees, which is just barely above the equator, you are spinning at 463.3 meters per second. And that's the velocity at that angle, or that particular latitude. I'm carrying out these decimal points to a ridiculously long length because down here at the equator, these numbers are so similar. If I end up rounding up any, then instead of getting a smaller radius, as I go higher in latitude, I end up getting a larger radius. So what I do is just leave these numbers in the calculator. I don't change anything, and I just keep multiplying or dividing by that number. Okay, next page. Okay, so that was the velocity at that angle. Now I'm going to do the velocity at 0 degrees, the equator. There's the circumference of the Earth. Turn that into meters per second because the Earth spins around every 24 hours, and we end up with 463.3102 meters per second at the equator. Subtract the number I just came up with here, 463.30991 for the, where was that angle here? Right here, 0.1798 degrees. We end up with 0.0003 meters per second. In other words, if you're near the equator and you're shooting either toward the pole or toward the equator, you and the target are both spinning at nearly the exact same velocity. So Coriolis effect does not matter in that situation if you're shooting north or south. But if you're shooting east or west, you may have to either aim high or low on the target, and I'll cover that at the end of the video. Okay, next page. Like I said earlier, I don't want to make any assumptions because, for example, those velocities are almost identical, but I don't want to assume anything by that, so I actually want to go through the math to see how much of a difference it actually makes. So let's say we're shooting an artillery shell at a 45-degree angle to get maximum distance. All I'm going to do here is just get the velocity in the x direction, so I'll know for how long that artillery shell is in the air. So cos 45 equals adjacent over, I'm just going to make up an average velocity here of an artillery shell. I'm going to call it about Mach 1, so about 343 meters per second. Speed of sound does change depending on temperature and wind. And I didn't bother to look up any particular velocities of artillery shells or rifle bullets, because you can get a muzzle velocity, but actually what I need is an average velocity, because that bullet is going to slow as it goes through the air. It'll encounter drag. So make up whatever numbers you want, but in this situation here, I think this might be a reasonable estimate, and that's what I'm doing with all these numbers. So the adjacent, which is velocity in the x direction, is 242.5 meters per second. That is how fast that artillery shell is traveling in the x direction. We're shooting at a target 20,000 meters away, and so 242 meters per second. Meter divided by meter cancels. We're left with 82 seconds. That means the artillery shell will be in the air for 82 seconds. And doing it this way, I didn't have to go through all the kinematics to find out exactly what the velocity was in the y direction and whatnot. And that's because all I need to know is for how long that bullet's going to be in the air, or that artillery shell will be in the air before it hits the target. So here, 82 seconds is how long that artillery shell will be in the air. 1 second equals 0.3 millimeters from the previous calculation, because basically the fast train is traveling 0.3 millimeters per second faster than the slow train. It just comes out to be 25 millimeters, or about 2.5 centimeters, which is about an inch. So if you're shooting at something either directly north or south near the equator, shooting at something 20 kilometers away, about 12.4 miles, in this situation, Coriolis effect does not need to be calculated. And again, that's if you're shooting north or south. If you're shooting direct east or west, I'll show that at the end of the video on what happens there. Okay, that's for shooting near the equator, where I said the cosines are almost identical. Now let's go up to near the poles. I'm going to show the calculations if we are above the Arctic Circle at a 70-degree latitude. In that situation, we're going to have a large difference in the cosines, which means the disks on which we are spinning will be spinning, or will be traveling at two very different velocities. And next page. Okay, now I'm going to deal with, or do the calculations for high latitude shots. We're at a 70-degree latitude up towards the North Pole, and we're shooting with the same angle of 0.179865 degrees. So you simply take 70 plus 0.1798 degrees to get the difference in your latitudes and to get your angle right there. And again, all I'm doing is taking an angle, turn that into cos, turn that into radius, turn that into circ, and turn that into the velocity of the effective disk on which the person or the target is spinning. So first I get the cos, which is the radius of the disk on which we're spinning. That'll be 2,179 kilometers. Multiply by 2 pi to turn that into a circ, multiply by 1,000 to turn kilometers into meters, divide by seconds in the day, so 60 squared and 24 hours in a day. And we get the velocity of the disk that is spinning at the 70-degree latitude. That's 158.462 meters per second. Now let's do it for, let's do the same calculations for 70.179865 degrees. Go through the same math. We get a different velocity of 157.09. We take the faster velocity minus the slow velocity. We get 1.37 meters per second. And that's the difference in velocity of our two trains, if you think of it as shooting from a fast train and you're shooting at a slow train. So the artillery shell will be in the air for 82 seconds, as I previously calculated. So this means if you do not account for Coriolis effect and you are shooting at a target 20 kilometers directly north or south at the 70-degree latitude mark, you will miss the target by 112 meters. In this case, we're shooting from south to north, which means we would need to lag the target or shoot behind it 112 meters. And if you're shooting toward the equator, then you will lead the target by 112 meters. As always, if you find any mistakes, let me know. This is just stuff I figured out. I'm going to switch situations here now. So instead of shooting north or south and changing latitudes with the projectile, I'm going to be shooting at the same latitude, so I'll be shooting directly east or west. In addition, I'll be shooting with direct fire, such as a rifle, instead of indirect fire with artillery. Also, I'm going to do the math for only 1,000 meters, because that's roughly the maximum distance for a lot of sniper rifles. When I was doing the calculations for artillery, I went out to 20,000 meters or 20 kilometers. So now I'm just going to do 1,000 meters. Before I do the direct fire situation, I want to cover indirect fire situation if you're shooting at the same latitude. First off, NP here stands for North Pole, so we're looking directly down on the Earth at the North Pole. Let's say the sun's here, here's the earth. This person is shooting from west to east. The earth rotates from west to east. It looks like if you're shooting at the same latitude, and let's just pretend this guy here is on the equator, it looks like the spin of the earth won't affect anything for indirect artillery. So for example, if the earth right here is not spinning, it's just stationary, here's a person right here, he shoots toward the target in the east. And let's say instead of doing a direct fire, he's doing indirect fire, so the projectile goes up and comes down. If the earth starts spinning, that will increase the velocity of the artillery projectile to the left, but the rotational velocity of the target will increase the same amount. So it looks like if you're doing indirect fire at the same latitude, you don't have to make any adjustments for Coriolis effect. So in this situation, we could do indirect fire from this point to this point. The projectile would be sped up because it's traveling with the rotation of the earth. And in the opposite situation, this person is firing from east to west, so the projectile will be slowed down because it's traveling against the rotation of the earth, but the velocity of the target will be increased proportionally as it spins up to hit the projectile. Okay, so that's for indirect. Now for direct. It looks like if the person is shooting right here and they're shooting in a somewhat straight line, say the bullet has a relatively flat trajectory. If that bullet's in the air for a few seconds, during that time, this target will have time to rotate down, so the bullet will strike the target in a higher location. Granted, if this person is shooting that bullet with the rotation of the earth, that bullet will be sped up and have an increased velocity from the perspective of a third-party observer, such as us. If we're in outer space and looking at that bullet, it'll look sped up, but the target will be rotating away from that bullet at the same rate. And maybe another way to think about this that's more intuitive, imagine like a tank tread. So this person would be actually way out here, and that bullet would come across, or it would fly in a straight path this way. The whole time the bullet is in the air, this target is rotating away from that bullet. So the bullet will tend to strike the target at a higher location. So I just sit here, same latitude, aiming east, and this is like a paddle wheel model. And in this situation here, we're aiming west, so the target will raise up to hit the bullet. And again, in this situation, the bullet will appear to be traveling slower because it's traveling against the rotation of the earth. But even though that bullet appears to be traveling slower from a third-party viewer, this target is rotating up to compensate for that. And thus it looks like that bullet will strike the target at a lower location. Here's another interesting thought. If you're up near the pole, this would be like being on a merry-go-round, kind of a domed merry-go-round, but still a merry-go-round. And we have this latitude line right here, so this dashed line represents looking directly east. But let's say the person is aiming to the northeast over here. And let's say that bullet will be in the air for several seconds, and if it's an artillery shell, it could be in the air for 1 or 2 minutes. During that time, this target will have time to rotate and spin around counterclockwise from our perspective. So it looks like in this situation, this person will have to aim a little bit to the left or a little bit to the north to catch the target as it spins around. And then the further south they go, the less this target will spin to the left, and the more it'll just spin away from the person, and it'll look like this situation up here where a person is just shooting on the equator. So here I'm going to show some calculations for direct fire at 1,000 meters if you're shooting on the equator. Let's say the target's 1,000 meters away. Let's just make up an average velocity for the bullet in the x direction. Let's call it about Mach 1, or the speed of sound, which will be 343 meters per second. 1,000 divided by 343, meter divided by meter cancels. We're left with seconds, so about 3 seconds that bullet will be in the air. Also, as with my previous examples that I did, I just made these numbers up. So I don't know what the actual average velocity is of various caliber bullets as they fly through the air over long distances. Feel free to plug in your own numbers if you get something more accurate, but I figure this will give us some ballpark estimates. And that's all I'm going for with this, is just a general gist of the situation. Okay, let's look at the Earth rotation rate. Earth goes around, spins around at 360 degrees about every 24 hours. 60 seconds per minute, 60 minutes per hour. So you take 360 divided by 24 divided by 60 squared. This equals 0.00417 degrees per second. That doesn't really tell us much. So let's say the bullet is in the air for 3 seconds. 1 second equals 0.00417 degrees. Therefore, a second divided by second cancels. The Earth will have rotated 0.0125 degrees while that bullet is in the air. That still doesn't tell us much, but what's fun about all these math puzzles is every step or every clue leads to another clue. So now I go on to the next clue. By the way, this will be about the third posting of this video because I keep catching little errors. And what's interesting about these math puzzles is if you were doing something like a jigsaw puzzle and you make a mistake and put a piece in the wrong place, you eventually figure it out because the picture doesn't match or the piece doesn't quite match perfectly. But with these math puzzles, you can make a mistake, get a wrong answer at the end, and you'll have no way of knowing that it's a wrong answer. So that just makes this whole situation more challenging. Okay, so at any rate, let's take our target at 90 degrees. I'm doing this example right here. So let's say the person's shooting at a target as it rotates either away from the person or towards the person. This target has now rotated from 90 degrees to 90 minus 0.0125 degrees. This equals 89.9875 degrees. Let's look at the sine value of that to see how much the target has shrunk down. I'll show more on the next page. Right here at 90 degrees, we will have the full radius of the Earth. So at 89.9875 degrees, we will have a sine value that is less than the radius of the Earth. So sine of 89.98749 degrees equals opposite over height. The height is the radius of the Earth in meters. Solve for opposite, we get 6,370.999.848 meters. Subtract that from the radius of the Earth, we get 0.152 meters or 15 centimeters, which is approximately 6 inches. That means that during those 3 seconds that bullet is in the air, that target is either rising up to meet the bullet, so the bullet will hit the target at a lower location, such as right here, or that target is rotating away from the bullet, so that bullet will hit the target at a higher location. That change in distance will be about 6 inches or 15 centimeters. And remember, this is on the equator. Technically, I should have used the equatorial radius, but again, this just gives us a ballpark estimate. Also, it looks like this 15 centimeters may not always be the situation. It looks like if you had a bullet with a relatively flat trajectory, then as that target drops down, the bullet will strike the target at a higher location. But if that bullet has more of an arc to it, as the target drops down, then the bullet will drop down also and may end up hitting the target in the same location. So I don't know. And same with the situation here. If you're shooting from east to west, if the bullet has a high arc to it, the target will rotate up. But as that target rotates up, it'll be hitting the bullet while the bullet is at a higher location in the arc. So it may not affect where the bullet strikes the target very much. I don't know.